Let's consider the following problem. A parallel plate capacitor has two plates um, with a separation D and a capacitance C. If I charge it with a plus Q and a minus Q on the two plates respectively, what is electrostatic energy? What is it if I move the two plates closer to D divided by 2? How would the answer differ and maintain constant potential difference between the two? Alright, so let's basically remind ourselves what the definition of capacitance is. Well, capacitance is basically C is equal to the charge on the capacitor divided by the voltage required to maintain that charge separation. Right? And basically for a parallel capacitor, it's basically C is equal to epsilon naught A over D, assuming of course that the space between it is just basically empty. Alright, and finally the electrostatic energy for a capacitor is basically U is equal to 1 half CV squared. Alright, so between these equations we can solve the following problem. Okay, so let's basically look at part A. What is electrostatic energy? So we're given basic Q and we're given C. Alright, so basically we need to know V in order to get the electrostatic energy. So that means basically that uh, V is equal to Q over C. So we plug this into here. So U is equal to 1 half C Q over C squared, which is just simply going to be basically Q squared over 2C. Now, the capacitance, new capacitance, is going to be epsilon naught A over D, okay, over 2, because I moved from D to D over 2. And so this is going to be 2 times the old capacitance, C, right? Okay, so whoops, I'm going too far ahead of myself. So this is the electrostatic energy, that's part A. Part B, what would it be if I move the difference between it? Well, I need a new capacitance, right? So just placing this in, what you end up getting is that U is going to be equal to Q squared over 2C, which is going to be now Q squared nu over 4C, right? Which is basically U old over 2. Alright, so basically we have the energy as a result of this. Now let's answer the final question. How would the answer if I maintain constant potential difference delta V between the two? Well, if that is the case, alright, we have to be careful then. Alright, let's look at this equation again. Now we maintain constant potential difference. U is equal to 1 half CV squared. V is constant now, so the only thing that changes is C. So it's going to be C. So is this the nu again? So C, plugging in C nu, this is going to be basically be 1 half 2 times C times V squared. It's going to be CV squared, which is twice what UO was. Okay, so it makes a difference. It makes a difference whether or not you charge it first and then you move them close together, or whether you basically maintain potential difference between you, like i.e. a battery, and then bring them close together. Right? Okay, I hope that was helpful.